Hello everybody, welcome to the next lecture on Material and Energy Balances course. Today we will talk about process parameters and variables. There are many parameters and variables which are used to define any process. So, the first and the most common one which is used are mass and volume. This basically defines what a system could be. These can be converted from one to another using density and specific volume. Density is defined as the mass per unit volume and specific volume is defined as the volume occupied by a unit mass of a substance. Basically, density is the inverse of specific volume. So, using density and specific volume, we can actually convert mass to volume and the other way around. Here you have been asked to calculate the volume of 10 grams of ethanol and the mass of 25 ml of ethanol using the density of ethanol which is 0.789 grams per centimeter cube. So, to calculate the volume of 10 grams of ethanol, we would divide mass by density. So, what we do here is 10 grams divided by density which is 0.789, we end up with a volume of 12.7 centimeter cube. If you look at this calculation, when we look at the dimensional aspect of it, the grams actually cancel each other off and the centimeter cube goes to the numerator, thereby giving you volume. When we calculate the mass of 25 ml of ethanol, what we do here is volume times density which is 25 ml times density which is 0.789 grams per centimeter cube. If you look at the third term, I would have used 1 centimeter cube per ml. Although numerically this conversion factor will not make a difference, writing this is a good practice which ensures that you do not make mistakes while performing conversions. So, the ml gets cancelled off and so does your centimeter cube, thereby you are left only with grams which is the mass. So, the final answer for this would be 19.7 grams. Please ensure that whenever you perform calculations, simple or tedious, write down the units along with the terms which you are using. Thereby you can minimize any errors in calculation which could creep up. Specific gravity is defined as the ratio of density of a substance to the density of a reference material. The reference material which is commonly used is water at 4 degrees Celsius. This is because density of water at 4 degrees Celsius is 1 gram per centimeter cube or 1000 kilograms per meter cube. So, when we use SI units and CGS units, these are round numbers which are easy to remember and apply. However, if you were to use American engineering units, the number is a little more cumbersome which is 62.43 pound mass per feet cube. Now, we looked at terms which are dimensionless and unitless in the last lecture. Will specific gravity be a dimensionless term? Yes, because it is a ratio of two densities. Obviously, the dimensions will get cancelled off and you will end up with a dimensionless term. So, the more interesting question is this a unitless term? The answer is no, it is not a unitless term. You need to use the units appropriately. To illustrate this, let us try an example problem. Specific gravity of nitric acid is given as 1.5129 20 degrees Celsius 4 degrees Celsius. Water at 4 degrees Celsius has been used as the reference. Calculate the density of nitric acid in grams per centimeter cube, kilograms per meter cube and pound per feet cube. So, the pound used here is pound mass. So, the specific gravity which is given has been written as 1.5129 20 degrees Celsius 4 degrees Celsius. This is a conventional way of writing specific gravity as the ratio of density of the substance at 20 degrees Celsius to the density of the reference material at 4 degrees Celsius. Here the substance is nitric acid and the reference is water. So, if we were to find the density in terms of grams per centimeter cube, then we should use appropriate units for the specific gravity of nitric acid. In grams per centimeter cube, the specific gravity of nitric acid would be given as 1.5129 grams of nitric acid per centimeter cube divided by grams of water per centimeter cube. So, when I multiply the density of water with this specific gravity, I would end up with the density of nitric acid which is 1.5129 grams of nitric acid per centimeter cube. If I were to calculate the density in terms of kilograms per meter cube, then the specific gravity for nitric acid should be written as 1.5129 kilograms of nitric acid per meter cube divided by kilograms of water per meter cube. Using the density of water as 1000 kilograms of water per meter cube, I can calculate the density of nitric acid as 1.5129 times 10 power 3 kilograms of nitric acid per meter cube. If I want to calculate the density in terms of pound mass per feet cube, then the specific gravity should be written down as 1.5129 pounds of nitric acid per feet cube divided by pounds of water per feet cube. Using the density of water as 62.4 pounds of water per feet cube, I can calculate the density of nitric acid as 1.5129 times 62.4, giving a final value of 94.4 pounds of nitric acid per feet cube. The units of pounds of water per feet cube cancel off to finally give you the units of pounds of nitric acid per feet cube, which would be the units for the density of nitric acid. As you saw, based on the units which we have used for the specific gravity, we use the appropriate densities for water to multiply, thereby getting the density for nitric acid in the different units. Another important term which is commonly used in addition to the mass and volume would be amount of substance. Any material which is coming in could be defined in terms of mass, volume or amount of substance. Amount of substance is a quantity that measures the size of an ensemble of elementary entities such as atoms or molecules. SI unit for such amount of substance is gram moles, or simply written as moles. The amount of substance mole is defined as the amount of a substance which contains the same number of constituent entities as atoms present in 0.012 kilograms of carbon 12. 1 mole of a substance contains 6.022 times 10 power 23 molecules or atoms. This is based on Avogadro's number. So, in addition to gram moles, you can also use units like kilomoles and pound moles. It is important for you to understand what these represent. 1 kilomole is equal to 1000 moles. This is something everybody remembers and understands because it is a simple conversion. 1 kilomole would then contain 6.022 times 10 power 26 molecules or atoms. This is based on Avogadro's number again. Similarly, 1 pound mole would be 453.6 moles. Thereby, 1 pound mole would contain 6.022 times 6.022 times 10 power 23 times 453.6 molecules or atoms. Knowing this is crucial for understanding American engineering system and understanding the concept of pound moles. Moles and masses can be converted between each other. How would you do that? What information would you need? You need to know the molecular weight of a substance. Molecular weight is basically the mass of 1 mole of a substance. So, it is calculated as mass of substance divided by the number of moles. Molecular weight for oxygen is 16 grams per mole. It is also expressed as 16 kilograms per kilomole or 16 pounds per pound mole. So, 1 mole of a substance, which is 1 gram mole of a substance, will weigh its molecular weight in grams, and 1 kilomole of a substance will weigh its molecular weight in kilograms, and 1 pound mole of a substance will weigh its molecular weight in pounds. To illustrate this, let us try and solve this example problem where we try to convert moles to masses. You have been asked to calculate the number of pounds which would be present in 10 moles, 10 kilomoles and 10 pound moles of ethanol, given that the molecular weight of ethanol is 46.1 grams per mole. 10 moles of ethanol would weigh 10 moles times the molecular weight, which is 46.1 grams per mole, giving you 461 grams. Converting this 461 grams into pounds, we would get 1.0163 pounds. 10 kilomoles would weigh 10 kilomoles times 1000 moles divided by 1 kilomole times 46.1 grams per mole times 1 kilogram by 1000 grams, giving you an answer of 461 kilograms or 1016.3 pounds. So, if you were to look at this calculation, what you would observe is I have converted this kilomoles to moles by multiplying with 1000 and converted the gram to kilogram by dividing it by 1000, and the moles, which is 10,000 moles, is cancelled off, thereby you get the final answer in terms of kilograms. So, this kilograms I have then converted to pounds. So, similarly I can perform the calculations for pounds also. 10 pound moles would weigh 10 pound moles times 453.6 moles divided by 1 pound mole times 46.1 grams per mole times 1 pound by 453.6 grams. So, the pound moles cancel off, so do the moles and so do the grams, thereby giving you a final answer of in the units of pounds. So, the final answer you end up with is 461 pounds, which is the mass of 10 pound moles of ethanol. So, based on this we see that the molecular weight of each of these substances in terms of grams per mole, kilograms per kilomole and pounds per pound mole can be used to convert them directly into masses. So, you can calculate mass in grams as molecular weight expressed in terms of grams per mole times the moles, and mass in kilograms can be calculated as molecular weight expressed in terms of kilograms per kilomole multiplied by the kilomoles. Mass in terms of pounds can be calculated as molecular weight in terms of pounds per pound mole times pound mole. Another parameter which we need to know about when we talk about any process is the composition of a mixture. So, we initially looked at mass, volume and moles, or the amount of substance, which are all the measures of magnitude. We also need to know the composition of the streams which are entering and leaving the system. For this we use two most common terms. The first one is mass fraction. It is the ratio of a mass of a substance to the total mass of the system. So, this is conventionally written as X. You also have mole fraction, which is conventionally written as Y, as the ratio of the number of moles of a substance to the total number of moles of the system. So, these mole fractions and mass fractions can also be written as mass percentages and mole percentages by multiplying these values by 100. Here is an example problem where we can try to calculate the mass fraction and mole fractions for a mixture which has been given. If 10 kilograms of acetic acid is mixed with 90 kilograms of water to prepare vinegar, what are the mass and mole fractions of acetic acid and water in this mixture? You are given that molecular weight of acetic acid is 60.1 kilograms per kilomole and molecular weight of water is 18 kilograms per kilomole. To make our calculations easier, we will construct this table. The first column contains the components and the second column gives us the information on the masses which have been provided to us, and based on these masses we can then calculate the mass fraction. The fourth column is the molecular weight which has been provided to us. Based on the molecular weight and the mass we can calculate the number of moles, and based on this we would be able to calculate the mole fraction. So, the problem statement gives us that 90 kilograms of water and 10 kilograms of acetic acid are mixed. So, this term would be 10.0 and this would be 90.0, giving us a total mass of 100 kilograms. So, the mass fraction of acetic acid would be 10 divided by 100, giving you 0.100. Similarly, the mass fraction of water can be calculated as 90.0 divided by 100.0, giving you 0.900. The summation of these two mass fractions would give you unity, which is 1.000. The molecular weight for acetic acid is given as 60.1 kilograms per kilomole and 18.0 kilograms per kilomole. Based on this, we can calculate the number of moles of acetic acid as mass, which is 10.0, mass which is 10.0 divided by 60.1, giving you a value of 0.166, and mass which is 90 kilograms divided by the molecular weight, giving you a total number of moles of 5 moles. So, you are left with a final answer which is the total number of moles as 5.166. So, using this you can calculate the mole fraction as 0.166 divided by 5.166, which would be equal to 0.032, and the mole fraction of water would be 5 divided by 5.166. So, the numerical value for this would be 0.968. The summation of these two would give you unity again. So, this is how you would go about calculating your mass fractions and mole fractions. In case you have not been given the masses and only the mass fraction has been given, what you can do is you can assume that the total mass of the mixture is 1 kilogram or 100 kilograms, and use the mass fraction to calculate the mass of these mixtures, mass of these components in these mixtures, and then convert those masses to moles and still calculate the mole fraction. Because mole fractions are ratios, the final answers you get will still be applicable based on, and it does not depend on any value you assume for the total mass of the mixture. In addition to composition of the mixture being defined as mass concentrations and mole concentrations, you can also have concentrations. Concentrations are basically mass or moles of a substance per unit volume. So, it is written as mass concentrations, which is mass of a substance per unit volume, and mole concentrations, which is moles of a substance per unit volume. Another term which is used for defining concentration is molarity. Molarity of a solution is defined as the molar concentration of a solute expressed in terms of moles of solute per liter of solution. So, this is moles of solute per liter of solution. You also have molality, which is number of moles of a solute per kilogram of the solvent. So, please understand that molality uses number of moles of the solute in the numerator and kilograms of the solvent, not the solution, but the solvent in the denominator. You also have parts per million and parts per billion, which are also used. These are discouraged by scientific community, but it is still widely used in many domains. Traditionally, billion in US is 10 power 9 and billion in UK is 10 power 12. This can cause confusion, and it is better to avoid ppm and ppb terms as much as possible. Flow rate is a term which is used for defining the flows which are entering and leaving the system. So, you have the rate at which material flows, which can be expressed as mass flow rate, which is mass flowing per unit time, or volumetric flow rate, which is volume flowing per unit time, or molar flow rate, which is moles flowing per unit time. Just like how you convert mass and volume between each other, you can convert mass flow rate to volumetric flow rate using density. So, mass flow rate is equal to density times volumetric flow rate. You can also convert molar flow rate and mass flow rate between each other using molecular weight. Molar flow rate would be equal to mass flow rate divided by molecular weight. You need to understand that this can be used only when the molecular weight of the substance is known, and in case you have a mixture, it might not be appropriate to use this directly unless you have the average molecular weight of the mixture. Linear speed can be calculated as volumetric flow rate divided by cross sectional area. So, when you have any material flowing through a pipe or through some stream, then the cross sectional area of the flow can be used in the denominator, and you multiply it with the volumetric flow rate. So, basically you do volumetric flow rate divided by cross sectional area to obtain linear speed. As an exercise, I would like for you to perform dimensional analysis to verify if these 3 equations are dimensionally correct. So, check whether mass flow rate can be written as density times volumetric flow rate, molar flow rate can be written as mass flow rate times divided by molecular weight, and linear speed can be written as volumetric flow rate divided by cross sectional area. Now that we have looked at all the parameters which define the amounts and flow rates and so on, the condition of a process can be defined based on 2 major things, which are temperature and pressure. Let us first look at what temperature is. Temperature is the physical quantity which expresses the hot and the cold condition of the system. It is defined as the measure of the average kinetic energy possessed by the molecules of a substance. It can also be defined as a property of the state of thermal equilibrium of the system with respect to other systems, because temperature relates to the capability of a system to transfer energy as heat. These 2 definitions are actually different, and when we solve energy balance problems, you would be able to understand and appreciate how these 2 definitions are actually uniquely different. There are 4 units for temperature which are commonly used. You can have Celsius and degree Fahrenheit. You also have degree Rankine and Kelvin, which are commonly used for measuring temperature. You have the relative scales, which are the Celsius and degree Fahrenheit, which are based on specified reference temperatures. So, the reference temperatures which are used for Celsius and Fahrenheit are based on the freezing point of water, which is 0 degree Celsius and 32 degree Fahrenheit. You also have absolute scales, which are based on the absolute 0, which is the lowest temperature that can be achieved as the 0 point. So, degree Rankine and Kelvin use absolute 0 as the 0 point. Degree Rankine uses 0 degree Rankine, which is minus 459.67 degree Fahrenheit, and Kelvin uses 0 Kelvin, which is minus 273.15 degree Celsius. For ease of use, these 2 values are rounded off to minus 460 degree Fahrenheit and minus 273 degree Celsius while performing conversions. We need to also understand that the term degree, which is 1 unit degree in a Celsius and Kelvin scale, is not the same as the degree which is referred to in Fahrenheit and Rankine scale. If you were to use delta degree Fahrenheit, delta degree Rankine, delta degree Celsius and delta Kelvin as the unit temperature differences in Fahrenheit, Rankine, Celsius and Kelvin, then what you would have is delta degree Fahrenheit will be equal to delta degree Rankine, delta degree Celsius will be equal to delta Kelvin, but delta degree Celsius will be equal to 1.8 times delta degree Fahrenheit, and delta Kelvin will be equal to 1.8 times delta degree Rankine. However, the symbols delta degree Fahrenheit, delta degree Rankine, delta degree Celsius and delta Kelvin are not commonly used. The delta is suppressed. So, this means degree Fahrenheit, degree Rankine, degree Celsius and Kelvin, which are used in the units, could either represent the actual temperature or the unit difference in temperature, and this must be interpreted appropriately. If you want an example, the best thing you can look up is the units for specific heat. Specific heat capacity can be given in terms of per Kelvin or per degree Celsius, where it is actually the temperature difference which is being looked at and not the actual temperature itself. These temperature units can be converted amongst each other using these formulae. If you are already familiar with them, great. If not, please go through them, try to convert these numbers between each other and have a feel for how temperatures can be converted from one unit to another. Pressure, which is the other parameter which can be defined for a system, is the ratio of perpendicular force to the area. SI unit for pressure is Pascal. There are many other units which are commonly used: atmospheres, bars, torr, mmHg and pound force per square inch are all common terms for common units for pressure. So, here I have given you the conversions which can be used directly for converting these common terms to SI units and other units. Like temperature, pressure can also be expressed in terms of absolute or relative pressures, and absolute pressure is usually given as PSIA and relative pressure is given as PSIG, which is the gauge pressure. Absolute pressure is nothing but the sum of gauge pressure and atmospheric pressure. So, this gives you all the fundamentals you need to understand the process parameters and variables which are used to define or describe any chemical process. In the next lecture, we will look at what we can do to perform material balances and what are the fundamentals which we need to understand to perform such material balance calculations. Thank you.